Welcome to week 5 for the course ISDA 609. So this chapter we're going to cover discrete probabilistic modeling. So we would cover how to use probabilistic modeling with discrete systems, modeling component and system reliability, followed by linear regression. So we talked about models using proportionality. And in this chapter, we would allow the constants of the proportionality to vary in a random fashion rather than to be fixed. So essentially, y equal to kx, this k is no longer a constant. So for rental car model, so here it says, okay, it could, so essentially it could be in two states, either 1 or 2, and there's some transition probability from 1 or 2, 1 minus p, or from 2 to 1, 1 minus q, from 2 to 2, q, and from 1 to 1, p. And then in the long run, approximately 57% of the cars will be in Tampa and 43 will be in Orlando, which actually this curve represented the example. So upper curve is the relationship we discussed. It's 0.4 to stay at Pn and 0.7 to stay at Qn and 0.4%, 0.4 possibility to go to Pn. And these, if we could model the possibility of voting tendencies, we could look at the long run probability that how many would be voting for Republican and how many would be Independent and Democrat. I'm not sure if this is a valid example in the sense that it actually represents the real data, but in general, this is just a a modeling method. So if we want to model a system and we want to measure the reliability of the system, then if we let ft be the failure rate of an item component system over time t, so ft is the probability distribution function, then we can use rt to model the reliability of the system. And then for series system, we could use the multiplication to get the system reliability. While for the parallel systems, we can use R1t plus R2t minus R1t times R2t. Interesting, right? This is something that we learned in Ohm's law. Or it could be a combination of both. For basic linear regression, yi equals to a times xi plus b, and then we can solve the problem to solve for a and b using partial derivatives. Yeah, read the examples and I'm sure you would understand it. And then at the end, we could use a couple of metrics to measure the error. Sum of squares error, SSE, the real world observation minus the predicted value based on our model squared and then sum it. So it's called sum of squares. And then correct sum of squares, SST, the real value observed minus the average of all the values. Regression sum of squares using SST minus SSE, we can get SSR. And coefficient of determination, R squared, very important concept that will be used to measure how good the fit is, which is R squared equal to 1 minus SSE over SST. So possible patterns of residuals could be fan-shaped, could be a linear relationship, could be curve linear. But all these are not ideal in the sense that we don't really want. We want to look at the residual plots and it look random. This is homework for this chapter. Thank you.